as it increases?
Let's see. Remember the way that it's defined is in the cold mode QC over work in. So yeah, the idea is for a certain amount of work in, if you are able to extract more heat,
That's more efficient.
yeah, so that means it's more efficient. So as the number goes up, it gets more efficient. So how would you say the second law of thermodynamics? With efficiency, the way to say it is, you can never have a 100% efficient engine. With refrigerators or heaters, how do you word it?
What is
You see, can you say the same way? You can never have a 100% coefficient of power.
Would
No.
it be infinitely large? You can't.
Exactly. You can never have it infinity. It's the other way.
Yeah.
Because as they get bigger, they're more efficient. So you can never, it's always less than infinity. In other words, if you put in 0.0001 joules of work and you're able to dump, 10 to the 6 joules of heat into the room, right, to keep you warm in the cold weather, imagine what the efficiency of that would be. 10 to the 6th over 0.001. The coefficient of performance would be 10 to the 10th, but you can never have that. So it's the other way around. You say you can still say you can never have 100% efficient refrigerator, but the more technical way to say it is you can never have a coefficient of power that's infinity. That's the equivalent to say it's never 100% efficient. You see? So what are some typical efficiencies? Well, here it tells you typical COP values for air conditioning and heat pumps are in the range 2 to 4, or about 1/10 of the theoretical maximum. So that's typical efficiencies. How do you derive the theoretical maximum? You change the QH. Remember what the equation was? What's the theoretical maximum? QC over work in is Q hot minus QC, right? 1 over what? QH over QC minus 1. How do you know what the theoretical maximum is? Change T hot to T cold. This is the maximum coefficient of power. 1 over T hot over T cold minus 1. So if you run the refrigerator as a Carnot cycle, right? It's going to be 1 over TH minus T over TC minus 1. But that's too high of an efficiency. Even the Carnot cycle efficiency is not infinity, right? It's maybe the Carnot cycle efficiency is 20, let's say, COP. But the realistic, you see what it's saying? The realistic COP is about 1/10 of the Carnot maximum. So in other words, in real life, this thing comes out to be 1/10 of this. You see?
Wow.
Like for car engines, the Carnot engine is maybe 60%. But then realistic cars are 20% efficient. So you say they're 1/3 of the efficiency of the maximum. You see? Cars are 1/3. They're running 1/3 as efficient. Okay, but electric cars, maybe they could be 40-50%. I have a Tesla now, but would I test the efficiency of my Tesla? Well, how long I can drive, then how long it takes me to charge, and then I would have to do some kind of calculation to derive the efficiency. But it's not going to be past 60% or maybe 70%, But it's going to be closer to that than a gasoline-based car. You see. Today I just took a picture of a car. It was a Toyota Mirai, fuel cell it said on it. So that was the first car that I've seen that's actually hydrogen fuel cell. And they might even be more efficient than electric cars. Yeah. Okay, now let's discuss the Carnot cycle. Okay, so you've got the we'll do the Carnot cycle. The Otto cycle and the Stirling engine, the Stirling cycle. And then there's many other cycles, you know. Carnot cycle is you start with a high pressure, low volume, then you isothermally expand it, then adiabatically expand it, then isothermally compress it, and adiabatically compress it. You see? So you can say the start of the cycle is at the left top corner. That's why they call that point 1. Point 1, isothermal, adiabatic, isothermal, adiabatic. So just to give it some numbers, let's say P1 is 3 atmospheres. V1 is 1 meter, let's make it 10 meter cubed. The number of moles of the gas, let's say, is 10. So then let's say V2, this is going to be V2, right? Let's say it's 20 meters cubed. Right? Then we can start doing a problem with this. So if the number of moles is 10, and we know that it's 3 atmospheres, and we know the initial volume, what can we calculate from that? P1, V1 is nRT1, right? So then what's going to be the pressure? 3 times 1.013 times 10 to the 5th, right? So we can call like this is like an example. Times the volume is 10 meters cubed. The number of moles is also 10, right? So it cancels out. Gas constant 8.314, T1. So from there we can calculate the initial temperature of the gas. Okay, let's see. The 10 and the 10 cancels, right? So you just divide that by 8.314. So, oh, it's high. Temperature is 36,552 Kelvin. Let's see. It's probably too high. The volume would have to be, oh, you know what? Maybe the volume should be 0.1. It's way too much. Not realistic, guys. In other words, if you have a 10 meter cube, then you cannot have with 10 moles, just that is not going, 0.2 meters cubed. So let's see if this one was 0.1 instead of 10, then your answer is going to be, okay, that's more realistic. T1 is 365.5 Kelvin, which is hotter than room temperature, right? So you start out with a hot gas, and now you're going to expand that isothermally. That means it's going to stay hot, but the volume is going to increase and the pressure is going to decrease, right? So then what's V2 going to be? So you're going to use the similar skills that you know from chapter 20 and 21, right? But now we're just applying it to a particular kind of engine. That's the only difference. So now you're going to say P1 V1 is P2 V2, right? Because it's isothermal. So then you have here 0.1 V1, and then P2 we don't know, and V2 is double V1, right? It's just double that. So then what should happen? The pressure should be 0.05. No, hold on. This is P1. P2 should be, yeah, P2 should be 0.1 over 2. Let me see how, I think I did. P1 is 3 atmospheres. V1 is 0.1 cubed. P2 and V2 is 0.2 meters cubed. So what's P2 gonna be? Oh, okay, basically 1.5 atmospheres, right? Half of the pressure. 1.5 atmosphere. So graphically, it's actually, if this is 1, and this is 2, and that's 3, right? So where should it be? Where should it be? 1.5. Oh, you see? So my drawing is wrong. That's why I'm kind of particular about the graph, because I want it to be realistic, you see? So then if I start here, it's around right there. The volume, well, you know what? My picture here is not realistic too. If this is double that, what should that be? Something like this. V1 point meter cubed, right? This and this is double that, right? Like that. Yeah, just draw it to scale so it's kind of nice. And now you have here P1. So now we go halfway. There you go. So it's steeper than how I had drawn, right? So this is going to be, always put the temperature at the corners. T1 is 365.5. What's the temperature here when it reaches the second point?
Same.
Yeah, so T2 is 365.5, but the volume is double and the pressure is 1.5 atmosphere. Right? Then it's going to be adiabatically increase. So now let's say we give you the, this is 0.25 meters cubed, like halfway. It adiabatically increases to 0.25 meter cubed. Now what's the pressure and what's the temperature? How do I know? What's the equation for the adiabatic?
What
P1 V1 to the gamma.
what type of?
Yeah, then you're going to have to ask what type of gas it is. Was that on, yeah, that was on the last test, right?
Yeah.
Test 4, okay, okay. So how about if it's diatomic? Remember there were exceptions to the rule, but the typical diatomic would be what? 7/5. 5/3 is monatomic, 7/5 diatomic, 9/7 polyatomic, right? So it's going to be 7/5, which is 1.4. So then the initial pressure is going to be 3 atmospheres. Or you know what, I can take it from there. What am I saying? 1.5 atmospheres is the initial pressure right here. So I should actually put it like this. P2 V2 to the gamma, P3 V3 to the gamma, right? Because it's the second and the third point. So then you have here V2 is going to be what? 0.2 to the 1.4 power, P3, and then V3 is going to be what? They told us 0.25 to the 1.4. So how do I find P3? And just a simple ratio, right? Okay. P3, 1.0975 atmospheres. So visually, so this is wrong. Visually it should be, this is 0.25, so a little bit above 1. like this. Right? Remember, adiabatic is steeper than isothermal. Right? So a bit more steeper. Okay, then you need a what? Isothermally compress it back to some volume such that you can then adiabatically go back, right? So what does that volume have to be? Something like this probably. It's going to be almost a very thin curve. Then you go back like that. So what is the volume there and what is the pressure? Well, what's the temperature here, by the way? T3. We don't know that either because it's not isothermal. How can we figure that out? You could go back to the PV equals nRT, and then you say P3 is going to be times 1.013 times 10 to the fifth. V3 is going to be 0.25, 10, 8.314. And then T3 is going to be, then solve for that. So you can put it in that corner, you see. So, $334.3 Kelvin. So what happened? It cooled, right? 334.3 Kelvin. The pressure dropped, the volume increased, but it cooled in the process, right? Then how do we find that, V3? Well, from here to here it's isothermal. So actually, this is actually V4, right? V4, P4, right? So going back, it's isothermal, so T4 should be 334.3 Kelvin, right? But then what's V4, P4? Well, I don't, because there's two unknowns. I don't know that what they are. But I do know from there to back to here, it has to be adiabatic. You see? So I know two restrictions that they have to have. P4, T4 needs to equal P3, V3, right? P4, V4 needs to be P3, V3, because that one was isothermal, right? But then from here to here, the other restriction is what? P4, V4 to the gamma is equal to what? P1, V1 to the gamma, right? So it must meet those two restrictions to be isothermal and then adiabatic, right? So now we're going to put these together. How do I do that? Well, I can just solve for one of them, like I can say V4 is P3 V3 over P4. Then substitute that into here. P4 is I feel like it's easier to substitute for for P, right? Because if I substitute for V, I'm going to have to raise all of that to the power gamma. Why don't we do it the other way? I'm going to say P4 is P3 V3 over V4. Make it a little easier for you, right? Then substitute it into here, you don't have to raise it to the power gamma, right? So then P3 V3 over V4 to the power of V4 to the gamma is P1 V1 to the gamma. There you have it. You see? So now P3 is equal to what? 1.0975 atmospheres. I might be able to just leave it as atmosphere instead of changing it to Pascal. So 1.0975 atmosphere. V3 is going to be what? 0.2. V4 is going to be let's see, V3. Oh, V4, we're solving for that, right? So this is actually going to be V4 to the gamma minus 1, right? V4 to the gamma minus 1, right there. So then I just put P3, V3, hold on, did I do that wrong? You gotta be careful here. This is my P3. What's my V3? Oh, V3 was actually 0.25. See, let me do a better job here. V2 is 0.2, V3 is 0.25. You see? See how the graph affects what I'm doing? I'm purposefully making those mistakes. See, now you don't know if it's on purpose. But those are on purpose because, you see, I'm showing the graph, how you draw it will affect you. So then visually, I need to be able to see this and see what's going on, right? So P3, V3 should be 0.25. V4 to the gamma minus 1. Now P1 is 1 atmosphere. V1 is 0.1 to the gamma, which is 1.4. Okay, so then what do you have here? 1.4 minus 1 is going to be what? 1.4 minus 1, 0.4, right? Then how do you solve that? Well, just do this and bring everything here. V4 to the 0.4 power. What's that going to be? So 0.1 to the power 1.4, that's that. Divide that by 0.25, divide that by 1.0975. And then I get 0.145. So then how do I solve for V4?
Oh, just say to...
Why don't, one way to do it is raise both sides to the power 1 over 1.4, or you could just do ln,
just do...
right?
Yeah.
Then you say no, ln is not going to help.
To the 5 over 2 and that's it.
No, ln is not going to help.
To the 5 over 2.
It's just, better just to go V4, 0.4 over 1 over 0.4. 0.145 over 1 over 0.4. And 1 over 0.4 is 1 over 2/5, which is 5 halves. Right? What is it?
P1 is it?
Yeah, you see I did wrong. All of that is on purpose. See, P1 is 3 atmospheres. And then you got 0.1, okay. So then you're gonna have this times 3. And then 0.435. Is it okay if it was in atmospheres? Or should I change it to pascals? Yeah, this is atmosphere and atmosphere.
Yeah.
It cancels. Let's see. So you're okay. So then you're going to have 1 over 0.4, which is the same thing as saying 5 halves. So 0.435 to the power 5 halves is 2.5.
0.125.
0.125. V4, 0.125. So visually, around right here, right? 1.1 and a quarter. So somewhere here. Nice. And then from there, go back adiabatic. So then all that's left to do is find P4. If V4 is 0.125, what's P4? Then you just say P4, V4 is P1, P3, V3. Right? In other words, you go back to this equation. It's like a two system equation, you know. So then you go back to that equation and you say P4, V4 is 0.125, P3 is, which one was it? Oh, I erased it. 1.0975 times V3, which is 0.125. Right? Do I have everything right? P3.
Wait, isn't that V4?
Which one?
For V3, you put V4 instead.
let's see, V3 is going to be 0.25.
Yes.
And then P3 is 1.01975. Okay, so this is 0.25, right?
Yeah.
Then V4 is the 0.125. Okay, I think that's it. So now, T4 2.195, and you just put that into the graph. Oh, wait, 2.195, so, oh, that's all the way up here. Wow, this is a thin graph. Wow, like that. Then, this kind of looks weird, huh? It looks like this, but it's a very flat version of this. You see? So now that we've got all the numbers solved, what is the efficiency of this engine? Okay? How do I find that? Well, in order to do that, because here's what the problem is likely to say. Find the Q, the work, and the QH here. In other words, find QH, QC, and work here. Find here, same things, QH, QC. And then it might also say, find the change in entropy in each cycle. Right? Change in entropy, change in entropy, change in entropy, and then change in entropy. Right? So then, in stage, we can call this stage 1. It's a 4-stage engine, the Carnot engine. In stage 1, what do we have? Isothermal. Q into gas, remember first law of thermal? Q into gas is work out plus delta E, right? So then what's going to happen? In the stage 1, what process was that? Isothermal. So is there a delta E? In isothermal, does the temperature change?
No.
Okay, then delta is 0, right? And then what's going to happen? Q in is going to be work out. So what's the work done by the gas in an isothermal process? The integral of PdV, right? And then P is going to equal what? nRT over V, right? nRT over V, dV, right? And then remember, temperature is constant in isothermal. So Q in is going to equal nRT1 ln of V2 over V1. So in an isothermal process, that's always the equation of work. nRT, because T stays constant, times the ln of the ratio of the volumes. So then in my case, it's 10 moles, 8.314. T1 is 365.5. ln of 2, because the volume doubled. You see? $21,000, so I'm going to write it as a kilojoule. Q in is going to equal 21.06 kilojoules. Now, in terms of a heat engine, what is that? Engine, Q cold, work out.